So with bond polarity, this is a way of predicting whether you're going to have a ionic bond. So basically, if the absolute value of the difference between what's called the electronegativity, this is not something you ever have to figure out. That you're given this. There's a chart here. Let me show you. There it is. You would be given these numbers. So for example, oxygen's electronegativity is 3.5. Lithium's is 1, and so if you wanted to know, if lithium and oxygen were going to bond, what kind of a bond would it be? So you just take the absolute value of here. I guess I should just do that. Here, let's do that. So oxygen is 3.5. Got to remember this. Lithium is 1. So the way that you do that is, let's get to the. Here we go. So let's see, lithium, what did we say? Lithium was 1 and oxygen was 3.5. And so you just take the absolute value of the difference between those two. And so we get 2.5, right? And then you look on this table right here. Let me go back a little bit. This table right here, and let's take a bigger look at that. And so 2.5 is clearly greater than 1.7. So we would predict that the bond between lithium and oxygen was ionic. Just as a reminder, polar covalent is when the electron is shared, just like it is in covalent, but it's shared unequally. So the fact that this cloud is a little bit bigger than the cloud around this atom, so this is one atom, this is another atom, the one with the bigger cloud is sharing the electron, but unequally. It's taking a bigger share of the the electron, and this one is not taking as big. Whereas covalent, just plain old covalent, is when they're sharing the bond equally. All right, let's do another. So we got to go to the electronegativity chart. Oops, there we go. So here's our electronegativity. Since we already have oxygen on there, we'll do oxygen and nitrogen. Okay, so if you just look at those, it's 3 and 3.5. What would you predict if nitrogen and oxygen bonded together? I don't really, but let's go look at that. Let's get to this. All right, and so we already know oxygen's is here, I'll do it over here. Oxygen's is 2.5. I'm sorry, 3.5. And we know that nitrogen was 3, I believe, right? And so you take the absolute value of the difference between those, and you get an answer of 0.5, which is actually a little bigger than I wanted it to be, but that's okay. So with that, it's actually a little unclear what the electronegativity is going to, what that predicts. So let me explain what I mean by that. If you look at this table, see if it's exactly 0.5, that's covering both covalent. There's a little bit of overhang, if you see what I'm saying. Like if you got a difference of exactly 0.5, it could either be polar covalent or covalent, and so there's no clear way of doing that. So actually, those were two bad numbers. Let's do. How about this? How about phosphorus and sulfur? Okay, so you get 2.1 and 2.5. All right, I got to remember that. So phosphorus and sulfur, 2.1 and 2.5. Here, let's do that. So phosphorus 2.1 and sulfur 2.5. All right, so this is a good one. So we take the absolute value of the difference between them, and of course these are two nonmetals. So even before we do this, we would predict that that's going to be a covalent bond. So this, you get 0.4, You know, you don't even need a calculator for this one. It's kind of nice. So you don't. So it's 0.4. And if you look at the chart, go back to this chart right here. So since it's less than 0.5, that's clearly less than 0.5. What that is predicting is that is a covalent bond. Okay, so anywhere between 0.5 and 1.7 would be, you'd predict that it's a covalent bond. Let me say one more thing about this. It's very simple. It's nothing complex. What if we had oxygen bonded to itself? Okay, so we know that oxygen is 3.5, and so here's another oxygen, 3.5. So the absolute value of the difference, and this is true for anything bonded with itself, is 0, right? And so you go back to the chart, and that's clearly below 0.5, right? I mean, 0 is always below 0.5. And so here, let's take a quick look at that. So it's less than 0.5, and so that would be covalent. So something bonded to itself is a covalent bond. All right, at least that's what the prediction using the electronegativity gives us. All right, so enough of that. It's really simple. You're, like I said, you're always given. Oh, that's just another thing showing you. You're always given these numbers or this chart. So yeah, we just take any two and take the absolute value of the difference between them, and go by this chart right here, and it's just a way of predicting it. Okay, I guess I've said enough about that. Let's go on to naming. Well, we've already done the ionic compounds, so there's the ones for the transition metals. Remember, we have to put the Roman numerals. Let's see, and then when we get to covalent compounds, okay, so these are molecules, and the way that we name them is we actually use what are called Greek prefixes. We also end in IDE, right? And so these, remember, covalent compounds, forget about the polar covalent for just a moment. For covalent compounds, it's just nonmetals to nonmetals. We don't care whether it's polar or just polar covalent or covalent. When we're naming it, that doesn't really matter. So we end in IDE, and we use these Greek prefixes. Let me explain what the Greek prefixes are. Actually, I'll show you. Let me show you. So here are the Greek prefixes. You just have these handy when you're naming covalent compounds. Just keep in mind, covalent, it's a nonmetal to a nonmetal, like carbon to oxygen, for example. So if there's one atom, we use the word, we use the prefix, the Greek prefix mon. And it's kind of funny with mon. This is the only one that is reserved for oxygen. We'll see that in just a minute. Di means 2, tri is 3, tetra 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona is 9, and deca is 10. There's more than that, but that'll more than suffice. Okay, so mono is just 1. All right, so let's do some examples of that. Oops. All right, I'm going to start with some that we already know. For example, CO2. Okay, so remember, mon is reserved for if the second thing is oxygen and if there's only one of them. Okay, so we won't say. Well, I'm not even going to say it because that would be wrong. So the way that this is named, okay, so this is the chemical compound. This is the formula for the chemical compound is carbon. Okay, so you'd write the word carbon. Of course, there's only one carbon, and the second thing, the oxygen, there's 2 of them, so it's carbon di, right? Because di is the Greek for two, dioxide, right? Notice we end in IDE, right? That's very important with all of these. Okay, so that's called carbon dioxide, which you probably knew already, but that's just the proper way of naming that. All right, let's do another one, another very familiar one. What about CO? So again, there's one carbon, so we just say carbon, carbon. And then since the second thing is oxygen and there's only one of them, this is the one time that you use mon. So it's mon. And by the way, you don't say monoxide. The chemists don't like the two vowels butted up against each other, so it's just monoxide. Because it wouldn't sound very good, right? So carbon monoxide. Okay, so that's a fairly simple one. Let's do another one. Let's do H2O. Okay, so H2O, there's two hydrogens, so it's going to be dihydrogen, right? You just name the atom. Oops, hold on. Oops, I messed up. All right, so dihydrogen, and since there's one oxygen here, it would be monoxide. Okay, dihydrogen monoxide. That's a good one. So obviously we all know that as water, but this is the proper name of this molecule, dihydrogen monoxide. All right. How about this? What if we had H2O2? H2O2. This is very common. You find this in drugstores. It's also known as hydrogen peroxide. That's its common name, but the formal name of H2O2 would be, of course, dihydrogen. Dihydrogen. That's supposed to be a G. All right, dihydrogen, and it's dioxide, right? Because there's two. So dihydrogen dioxide. And that's kind of how this works. Let me point one thing out that's really, really important. In ionic bonds, remember, if we had excuse me, sorry, should have paused that. That just snuck up on me. On ionic bonds, when you have to reduce the subscripts to the least common factor. We never, ever, ever do this with covalent bonds. Okay, so just keep that in mind. All right, let's see. Let me think of another one. How about this? How about P3? I'm just making this up. P3F5. I don't even know if that's a stable compound, but of course, we could just at least name it. So there's three of these, so it's going to be three phosphorus, so triphosphorus. For us. All right, triphosphorus, and since there's 5 fluorines, it would be penta fluoride. Remember, you don't say fluorine, you say fluoride, because the second thing is in the periodic table. All right, and that's about it. These are the covalent ones are much easier to name than the ionic bonds. But the big thing is really just identifying, saying, oh, okay, this is a nonmetal. This is a nonmetal. All right.